but I can't. Or can I? So this is a cute little technique that I think Charlie knows very well because he wrote a paper with Mariska Crete on this a few years ago. And we adopted it for ZFOURGE, which is to essentially build composite SEDs. So what you do here is you have, in this case, we focus on redshift 1 to 3, around 4,000 galaxies, and you have imaging of 4,000 galaxies. Okay, so imaging. 30 to 50 bands for each one. So you have essentially a very poorly sampled spectrum of each galaxy. Now, if you start grouping them together, because they're all at slightly different redshifts, you start filling in the gaps, right? So I call it sort of the quantum mechanics way of building a spectrum. I'm sure that will get me into trouble with many physicists. But the idea here is that when you start grouping things together and they're all at slightly different redshifts, you start to fill in the SD, and you can build what's we call a composite SED, which is essentially a really coarsely sampled spectrum. So here's, and this is work that was really done by my former student, Ben Forrest. He's now a postdoc at UC Riverside. And so what you can see here are the purple points are the medians, and then the gray points are the actual measurements for each galaxy called analogs. And so here you have the UV, the IR. This is on the mid-infrared to far IR. It's a different scale because that's the only way we can get these points to show up, which is, and this is from, these are Herschel data, include Herschel data as well. So the resolving power nominally is for the best cases around 45 or so. And I just really want to stress that this is from imaging alone. Okay? So here, obviously a very young star-forming galaxy from the very strong emission in the blue. And then I just like to play this little video, which you can see as we move from the composite SEDs from very young all the way down to fairly quiescent. There's actually one composite that is a post-starburst galaxy. You can tell because it has a very sharp edge on the left-hand side and a very, sort of ski slope on the right-hand side. And so these bumps and wiggles, for the most part, are actually, you're also now seeing the emission lines. Right? So the emission lines, especially if they're very strong, they'll push up the total flux in that one filter, and you'll see it as a quote outlier. But when you start building them all together, you can see here these bumps and wiggles are actually real. And on this side here, for the dusty cases, there's a couple of dusty ones here. You'll see that for the dusty galaxies, these points pop up, right? Because all of that emission in the UV and or short wavelength optical essentially gets pushed out to the far infrared. And so I always call it like a water balloon. You squeeze one end, the blue end, and then the photons get pushed out to the other end. And you'll see it when you look at this full spectral wavelength coverage. Are we good with this? I think people have probably seen something familiar, especially with Charlie and Joel here. I suspect you've probably seen many of these versions. But I'm still always astounded by this because essentially what we're building, I'm at heart a spectroscopist. And so basically being able to do this from imaging to me still is very much like magic. But it seems to work. Well, I hope so because Ben wrote a whole thesis on it. And so here we have those SEDs, those composite SEDs, and this is from his last thesis paper in 2018. So we have them here from the top to the bottom. Once again, we're going from very strongly star-forming galaxies down to fairly quiescent galaxies. You can measure things like the Fokker-Balmer break or 4,000 angstrom break. You can see evidence of H-alpha, and in particular, there's one. Oh, use this stick here. There is this set of objects which have very strong emission. So this here is just a blow up, and that's blended there. These are blended O2 and O3 lines. Those are those little spikes that when I tested you guys earlier, you all passed with an A. That's this here. Right? And I just really want to stress that that's from imaging. Right? It's not spectra, it's just imaging. Imaging, fair enough, a very deep imaging, but still, imaging. So we found this population of objects that had very, very strong emission, very strong oxygen emission. And these things are very rare in the local universe. You may have heard of green peas. I think now there are also blue peas. Sorry, blueberries, not blue peas, blueberries. in the local universe, and these are objects that have very strong emission compared to their continuum. And so we were like, but they're very rare. They're like less than 0.3% or something of the local population. They were found in Sloan. So we were wondering, does this fraction actually increase? Because there have been other studies that find lots of emission on galaxies at higher redshift. And so part of our study was, well, okay, in our sample, we seem to find actually a good number being on the order of tens in our sample above a redshift of 2 or 2.5 or so. But then if we look at our sample below a redshift of 1.5 from ZFOURGE, there are essentially none. So even in our own study, now to be fair, there's some volume issues there because you can ask me about that later. But from the analysis that Ben did, we were able to demonstrate that the fraction does seem to increase. In terms of the magnitude of it increase is still uncertain. It'd be nice to get more data. But just to break it up into here, this is just from the imaging alone. Here you have, there's that 3727, so that's oxygen, and here's more oxygen. And so these are two composites. These are what we call the extreme emission line galaxies, simply because they have very strong, this is rest frame, by the way. Oh, I always have another good question. Sorry, just random things. Anyone want to guess what the O3 emission equivalent width for the Milky Way is? You're not going to remember anything about my talk except the random things I ask you. It is very small, yes. Great. Okay, that's actually about right. I'm sure. Nobody ever is able to answer this, so I'm not surprised that you guys figured it. It's around 5 to 10. It depends on where you look in the Milky Way and how you integrate light. I know that sounds kind of funny to say that, but it actually does depend. In the same way that we're not exactly sure what the star formation rate of the Milky Way is. So it's nominally around 1, but yeah. So I like to ask that because then I say, okay, it's still small compared to this number. Okay. So these are very different objects from what you think of as being even dwarf galaxies. And so then there's the next class, which is not as extreme, but even so, we're still talking on the order of a couple of hundred angstroms in terms of their equivalent width. So an order of magnitude higher than the Milky Way. So we went and wanted to study a bit more what these galaxies were, these very extreme emission line objects, and this is work that Joel was critical on. And this is work led by Jonathan Cohn, who's a graduate student, working with me. And so what you hopefully see here is that there's a blue squiggly line and then a purple one, and the purple one looks very different from the blue one. And essentially there's that H beta O3, it's blended, once again because the resolution is poor, so we can't resolve H beta and O3 separately, but you can see that there's very strong emission here. And you also see, I know it doesn't look like much, but there's also strong emission in the blue. So it's larger than it's in the UV, so the purple is higher than the blue. So these could be a great source of ionizing photons, for example, that we need to actually help the ionized universe. So these things have two things going for them, which is that maybe their number density, well not maybe, definitely their number density is increasing with increasing redshift, so that's good. So that means there are more of them at higher redshift, and then they also seem to be a really strong source of ionizing photons. So those are two characteristics that we need in terms of trying to understand the objects that we ionize the universe. Oh, sorry.
What is galaxies?
Sorry. Yes.
So when this peak occurs from the center of the galaxy, because there may be some kind of like interaction or whatever process that just kind of emits this H beta O3, right?
Yes.
So what is the...
So in terms of the emission and sort of like triggering some sort of star formation, is that what you mean?
Yeah, I'm just saying from the center of that particular galaxy, how far you go from that.
Oh, these are all point sources. Yeah. So in terms of the actual photometry, I would refer you to Caroline Stockman's paper in 2016. But nominally, these things are all they're smaller than an arc second across, and we do integrate. And so what we do is, sorry, just give a very short summary. Essentially what we do is we have to convolve all the imaging to the same seeing, and we use our best, highest resolution ground-based imaging, which is nominally about half an arc second seeing. And so we use that to then actually integrate the light from all the objects, and then that allows us to measure the photometry and then do all this fitting. In terms of whether or not they have neighbors, which I think is what you may be asking, we did look into that. I had one of my other students, Megan, just actually stack them and see if they were extended or had any evidence of like interactions, and we didn't see any evidence for that. Any evidence for major, any signs of major merging. Any major signs of merging. Does that answer your question?
Yeah, we can discuss that. I just wanted to know what is the physical source of that, right?
Oh,
How
what?
do you know
Where the star
process behind?
Oh, it's stars. I mean, this next slide may answer your question. So this is the SED for this one. This one is actually spectroscopically confirmed. The photometric redshift is listed there, but the spectroscopic redshift was essentially identical. I'll get into that in a sec. But here is a subset of filters. So here you have porcelainized optical filters. And because this is rest frame, that means that even the optical filters, once we convert it to rest frame, sample Gesundheit, the UV, and then here we have the IRAC filters as well. And you can see that for this one object, and once again, this is without Joel's help and Charlie's models, we would not be able to do this. But you can see how well the fluxes here, these are the fluxes that were actually measured versus the predictions from the SED fitting. And so we were then able to use this code, Prospector, to reconstruct the star formation histories of these very extreme galaxies. And essentially, I always think of this as a Rorschach test, but it's not. Hopefully what you can see is that the purple bits are offset, whereas the blue bits are fairly, it's a broad distribution, but they're fairly distributed